Am I audible? Okay. Cool. Hi, everyone. I'm Pratik Gandhi. I'm a grad student with Andrew Wetzel and the FIRE collaboration at UC Davis. And I'm broadly interested in low-mass galaxies across cosmic time, present day, high redshift. And today I'm going to talk about how if you take low-mass dwarf galaxies in the local group and their stellar fossil record, how that can be a powerful alternative probe for high redshift low-mass galaxies or faint galaxies compared to direct observations. Cool. So I want to start off with a big question about the epoch of reionization and galaxy populations in it that a lot of people have touched upon already. And that's what is the shape or slope of the faint end UV luminosity function at high redshifts, or correspondingly the slope of the low mass end of the stellar mass function. And Peter, in his talk on Tuesday, talked about this to some extent with universe machine. But this really is one of the central questions we want answered about reionization. So I'm showing here a redshift 7 UV luminosity function. There's some HST points over there, the scatter points. There's a best fit Schechter function with an extrapolation to the faint end. And there's some arrows showing HST, JWST magnitude limits, right? And the JWST limit is kind of outdated here. We know, especially with upcoming lensing surveys, JWST is likely pushing down to like -13, maybe -12 in UV luminosity. But if we're concerned with even fainter magnitudes, like the really faint end here, right, what does that start to look like? Does it steepen? Does it continue as a power law? Does it flatten off? A lot of people are very interested in answering that. And unfortunately, it seems like even with lensing surveys, we're likely unable to be able to directly observe galaxies at those extremely, extremely faint magnitudes, -8, -7, and so forth. And I want to say, there's so many people, we've heard a lot from them on Monday and Tuesday, doing really, really excellent work with JWST surveys. Getting these direct observations is incredibly difficult, and that's in particular because of how difficult it is, despite all the excellent work people are doing. This is why I'm interested in trying to use the local group as an alternative probe of this. Right, and so the reason the local group becomes important here is because of what's called the near-far reconstruction technique. You can think of it as near-field cosmology. But basically, if you get resolved stellar imaging of dwarfs in the local group and then reconstruct their star formation histories, their stellar masses, their UV luminosities as a function of time, right? An example of that is shown here from Wise et al. 2014, the star formation history for a local group dwarf. This allows you to figure out so these local group galaxies are faint even today. They're low in mass even today. So at higher redshifts, at redshift 7, 8, 9, they were even fainter, even low in mass. And so the local group stellar fossil record is therefore, for this reason, a potential probe of very faint galaxies at high redshift. Coming back to this luminosity function I showed here, again, keep in mind our sort of observational limits here of about UV luminosities of -13 or -12 in magnitude. If you now overlay what the fossil record of different local group dwarfs can achieve, we get something that looks like this, right? And so if you take Leo T, Draco, Sculptor, one of those very low-mass galaxies at present day, you're potentially able to push much, much further down the luminosity function at high redshift. And this is the idea I want to sort of talk about today. Naturally, there's still some outstanding questions about this idea. The first one that might come to mind is, okay, how well are we reconstructing these star formation histories, right? It's a hard process. You're fitting models to CMDs, and there's a lot of uncertainties there. I'm not really going to talk about this today. It is the focus of my upcoming work, so hopefully I can talk about it in the next few months. But the question I want to address is, if you take the local group galaxies that we see today, the dwarf galaxies, how well do they represent the population of low-mass galaxies in the proto-local group at high redshift? And how well do the proto-local group high redshift low-mass galaxies represent the global low-mass galaxy population at those redshifts? So it's these latter two questions that I want to address during this talk today. To unpack the first, as in the second question here a little bit more, here's a cartoon that I think is helpful. This is my very artistic representation of the local group dwarf galaxies as we see them today, the few tens of them that we observe. If for each one of them we reconstruct star formation histories, get stellar masses and UV luminosities at redshift 7, the picture looks something like this. it's a one-to-one mapping because reconstructing star formation histories gives you a single total stellar mass for a galaxy at redshift 7. It contains no information about how many progenitors that galaxy had at that redshift. Right? So the real picture likely looks something like this. And it's messy, it's complicated. All of those hundreds and thousands of low-mass galaxies in the proto-local group likely underwent complicated mergers and disruptions. Some of them merged amongst each other to form this population that we see at redshift 0. But a lot of them also just ended up forming the Milky Way and Andromeda and ending up in their stellar halos and their bulges, etc. And another way to visualize this is with these screenshots from one of the fire simulations. Nice, orderly local group with dwarf galaxies at redshift 0. Extremely chaotic, thousands of galaxies at redshift 7. Right? So because of those mergers and disruption, and because we don't know if those mergers and disruptions are mass-dependent, mass-independent, that raises a problem, which is when you take these present-day dwarf galaxies, reconstruct a high redshift stellar mass function or luminosity function and its slope, how much is that biased because of the effects of all of those complicated mergers and disruption? So to test that, I, as I've alluded to, turned to the fire simulations. A lot of people have talked about these already at the conference, but the few points I want to highlight here is that I'm taking about 13 Milky Way and local group-like environments with their low-mass galaxies. And because of our resolution, we're able to resolve galaxies down to fairly low masses, 10 to the 4.5 in stellar mass. Right? And at redshift 7, that gives you a very rough UV magnitude of about -9. So it's probing pretty far down the luminosity function. Finally, at present day, the mass functions and distributions of these dwarf galaxies in fire have been pretty well benchmarked against the existing observations from the local group. So it's a reliable population of local group dwarf analogs. All right, so coming back to this first question, if we have an incomplete census of the present day local group dwarfs, how well does that represent the high redshift population in the proto-local group at, say, redshift 7? So this is the first key result that I want to show today. I'm showing here a cumulative stellar mass function at redshift 7. The black line here shows that the true mass function for the proto-local group, all of the galaxies in there from our simulations, averaged across the sweep. Now, if I overlay the mass function at redshift 7 that you would get from this stellar fossil record of existing dwarfs at redshift 0, you get something that looks like this. Of course, this is normalized, like the total number of galaxies for the pink line is way below that for the black line, right? And that's fine. It's because of all of those mergers and disruption and lack of information about the progenitors. But what excites me is that the slopes here look pretty similar. And to quantify that a little bit more, here are the best fit slopes to the low mass end for both of those curves. Within 1 sigma, at least across our simulation suite, they agree really well. I'm showing the differential mass function slopes here. So you could read off the absolute slope here. It's like minus 1.85, which of course tells you something about the galaxy population. But again, the key I want to highlight here is how well these two slopes agree here. And this is true across redshifts as well. So spanning this redshift range of 6 to 9, we have, within 1 sigma agreement for the true slope of the proto-local group mass function in our simulations and the one recovered from the stellar fossil record. And that's why I'm saying that despite the effects of those mergers and disruptions, one key takeaway is that this near-far reconstruction technique still gives you a high redshift stellar mass function slope at the faint end that's pretty reliable. And these results are going to be in a paper that's coming out on the archive in a couple of weeks, so stay tuned for that. But I also posed a second question, which is then, if you're recovering the proto-local group low-mass galaxy population, how about the global low-mass population at those redshifts? So to do that, I'm now comparing to the high redshift suite of fire simulations that Jason Sun talked about during his talk on Tuesday. This is a pretty large sample of more than 5,000 galaxies at high redshift. So we think it represents some global properties pretty well. And importantly, at redshift 6 and above, it's been successfully benchmarked in terms of the mass and luminosity functions against existing HST observations at the time. I'm less concerned about the high mass end here. I know we've heard some talks about those, but especially at lower masses. So what this gives us is self-consistently within the FIRE model a benchmark of what the global stellar mass function should look like at redshifts greater than 6 that I can easily compare against without having to worry about comparing to observations directly. And so to provide my second key result, I'm again showing a cumulative mass function at redshift 7 and the corresponding differential slope here. The blue line here is for, again, the total galaxy population in the proto-local group from our Milky Way local group-like simulations that I already showed before. The red line here is now the mass function you recover from the stellar fossil record of existing present-day surviving dwarfs. And finally, if I overlay the stellar mass function in the high redshift suite and fire what's supposed to be global, quote-unquote, again, we get slopes that, although there is a fair bit of simulation-to-simulation scatter, agree within 1 sigma with each other. And this result also holds true across a range of redshifts. Right, so my second takeaway is that not only does this near-far technique give you an accurate reconstruction of the slope of the faint end mass function or at high redshifts for the proto-local group, it also does that for more global galaxy properties. And a caveat here, of course, that I've been talking about mass functions. We're also very interested in the luminosity functions. And in a paper that's coming out in more than 2 weeks on the archive, a second one, we're also going to be including corresponding luminosity functions for all of these mass functions so that we have that on record. Right, before I summarize my results, I'm just going to put it out there that I'm on the job market this fall. This is a representation of me in 2 months. So if you're interested in, dwarf galaxies, local group, high redshift, synthetic observations, resolved and unresolved of dwarfs in fire, please, I'm happy to talk to you, so please ask me about that. And finally, I'll summarize by saying this near-far technique is a powerful alternative to direct observations at high redshift for studying faint galaxies. And using the redshift 0, Milky Way, and local group-like simulations in fire, we've shown that this technique does a pretty good job in recovering the faint and or low mass end slope at these high redshifts. And then by also introducing the high redshift suite of fire simulations, we've shown that it also recovers the faint end or low mass end slope of the global galaxy population as well. Thank you.
Hi, very interesting, but I'm puzzled. I don't know the details of how these high-resolution fire simulations work at these redshifts, but what I'm worried about is that very likely the reionization of the universe is quite inhomogeneous. It probably starts first in the highest density regions, which is not where the Milky Way or similar galaxies are. They're in relatively low density regions. And as reionization occurs, it's going to prevent the formation of low-mass galaxies because, of course, it'll heat up the baryons, and then they won't be able to fall in or be retained. So the details of how that's done, eventually we can do self-consistently, but not for a long time because that's very complicated to do the radiative transfer. So should we really believe these high-resolution or early universe fire simulations? How have they taken into account the physics that I've just been describing?
Right. So yes, the question of when reionization occurs and how we're modeling that global reionization. Yeah. Right. How? Right. In patches. Yeah. Agreed. So yes. So in order to test that, we are also including in not the first paper coming out, but the second one, tests with different reionizing backgrounds as they're implemented in the simulation. So reruns of all of these simulations with different timing and different homogeneity of reionization. So hopefully that should give us answers for that. But the first tests for those are looking fairly self-consistent with the results that should. Yeah. Well, again, right. Yes, so I agree that you're quenching those low mass galaxies because of reionization, but then a lot of them are still surviving to present day or ending up merging into other slightly higher low mass galaxies. So we're still able to recover information about them from their fossil records. And even if the absolute slopes change because of the reionization model, the point I was making is that the recovery of that slope is still pretty good, even with the different reionizing backgrounds.
So I have a question in a similar line, but I think it's more of a clarification, which is, so how are you making the transition from a satellite stellar mass function to a volume-based field stellar mass function?
Yes, that's an excellent question. So I guess in this first comparison that I showed, right, these are comparisons of the mass functions within the same zoom-in simulations at redshift 7, the true population there, and then the inferred stellar fossil record. So it's within the same volume. Right? So here in this particular plot, I've not included any volumetric information. However, when I showed the second result, right, these are number densities, so I am including volumetric information there. And so we've thought a lot about how exactly to incorporate the volumes of these simulations, and I can talk more about that afterwards if you want. But yeah, we're trying to be as self-consistent across all the suites as we can with including volumetric.
All right, it's past the time when we're supposed to go to lunch, so let's thank all of our speakers this morning again. And see you back after the break.